Okay, so now that we've seen how we can use superposition to take the individual load cases, determine what stresses they're going to cause at our stress element, and then combine them to give us a good picture, a combined picture of what the stress state is at that point. Now we have to look at those combination of stresses, and because we're in two dimensions, you can have a normal stress in the x direction and a normal stress in the y direction, and some in-plane shear stress, tau xy. So we need to look at those shear or those stresses, that stress condition, and figure out what that means to us. And so we want to consider that state of stress at a point. Now, if we think of our sigma x and sigma y and tau xy as the components of stress for our stress condition, then what we need to do is figure out what orientation best reflects the worst case when it comes to that stress condition. So think of when we did forces, and say you have a force which is represented by a component in the x direction and a component in the y direction. Or let's say we gave you the x and the y direction and says, okay, figure out what force represents this. And so you would have to figure out some angle theta where the combination of the x and the y reflected the totality of that force. And it certainly would be in a worst case condition where the x and the y components collapse into that single force in the x direction only. Well, it's not really that much different for stresses. Our orientation that we're working in is typically convenient, and it's chosen out of a convenience to the mechanics, right? So along the axis of the beam and parallel to it, up, down. And so that axis is one simply of convenience. But what we need to do is now change our orientation or consider alternative orientations, which is going to change our description of the stress state. It doesn't change the stress state, just changes our description of the stress state so that we get it in a manner which describes it in the worst possible case, which is to say, what are our maximum normal stresses? What is our maximum shear stress that occurs at that point at some angle theta? And then that is the stress that we're going to need to compare to our material properties to decide if we have an adequate situation, or if we're doing a design, use that stress condition in order to design our part to be able to withstand it. Slightly more complicated than forces. Our stresses, of course, we know as we start changing the orientation, they're also related to the areas which start to change as you start to change your orientation. And so they don't have that straight vectoral manipulation that we would have with forces. And very specifically, stresses are a second order tensor as compared to vectors, which are forces, which are a first order tensor. So recall we talked about oblique sections before, so some of this should be just a review for you. And so if I bring up what we talked about in oblique section, and we see that we were able to take this axial load and determine that some combination of normal force, and shear force, or normal stress and shear stress, would describe that same condition at different orientations of theta. So now we're just going to make it a little bit more complicated, because instead of just a single force going off in the x direction, we're going to potentially have two stresses, one in the x, one in the y, and a shear stress in the xy. So here's our arbitrary orientation. Now I'm not showing a stress in the y direction, but we absolutely will be able to deal with a stress in the y direction. And again, this is just a reminder that our orientation is usually chosen out of convenience. And so you can imagine this is a piece of a beam which is running along the length. And so we're calculating our normal stresses in the x direction along the axis of the beam. and our shear stresses resulting from it. But now we need to make sure that we consider all our other alternative orientations in order to get our maximum normal and maximum shear stresses. And so here we have the XY axes. And so as we start to flip around our differential element and change our angle theta, and we see theta shown here, is we're going to come up with different normal stresses. In this case, we show it as sigma x prime and sigma y prime. And our shear stress is going to start to change as well as we change our orientation. So we have tau x prime y prime. So here's our stress element, and we need to do some derivation to figure out some equations that are going to allow us to do this transformation. And so we're interested at figuring out what our stresses are going to be on this plane theta as we start to change our orientation. And so we draw in our x prime and our y prime axes, and let's isolate that and turn it off here. And of course we're going to have a normal stress and probably a shear stress at that orientation. And so we'll label those as sigma x prime and tau x prime y prime. Now, to come up with these, it's just a matter of doing equilibrium, much like most of this course, is we're going to do equilibrium, and we have to account for the changing areas. So that's that oblique sections review that we did, and we can turn that into stresses. The stresses in combination with the area transformation, and we multiply those through, right? Stress times the area over which it's applied becomes a force, because equilibrium is applied to forces, not to stresses. And so in coming up with those forces, we're able to then go on and apply our equilibrium. So if we look at the areas, so we have our delta A naught is the area there. Then the area AC would be delta A naught cos theta. And our area CB would be delta A naught sine theta. So then to get the forces on that plane, we would take those areas and we multiply them by the stresses, which we already have labeled out. And so we can figure out that the forces on the transform plane are sigma x prime delta A naught and tau x prime y prime delta A naught. At the same time, if we look at what the forces are on the plane AC and CB, we see that the normal force, or the force in the x direction, is sigma x delta A naught cos theta, and our shear stress is tau xy delta A naught cos theta. And again, we go down to CB and we see the same sort of transition going on. So we have sigma y delta A naught sine theta and tau xy delta A naught sine theta for our normal and our shear stress. So now that everything is in forces, having accommodated that changing area, we can just treat them like vectors and do our equilibrium equation. So then to look at the transformation equations, this is just brought over from the previous slide. And what we're going to do is we're going to do the sum of the forces in the x prime direction and set it equal to 0. And so remember, x prime is going off on an angle lined up with sigma x prime in the diagram there. And so remember, these are all just simple vectors now because they're forces. They're no longer stresses. And so we have the normal force added to this, and it's going positive x prime direction, so it's just added in directly as sigma x prime delta A naught. And going in the other direction, we can ignore the shear stress on that plane AB because it's orthogonal to the direction, so it has no impact. There's no component in the x prime direction. So if we go down and we'll start at the shear stress on the plane CB, and so that's tau xy delta A naught sine theta. And if we multiply that by cos theta, we will have that component in the x prime direction. And then we'll do the same thing with the normal stress on CB. So we start sigma y, delta A naught sine theta is the force, and we multiply it by sine theta to get the component in the x prime direction. And then we do the same thing with the shear stress and the normal stress on the AC plane. And so we start with the shear stress tau xy, delta A naught cos theta, multiplied by sine theta to get the component. In this case, it's going off negative x prime. And we do the same thing for our last normal stress, sigma x, delta A naught cos theta, multiply it by cos theta in order to get the component going in that x prime direction, or the negative x prime direction. And we set those all equal to 0. And then if we go through some algebra and come up with a simplified form, we get this equation right here, which is sigma x prime is equal to, and there's really 3 parts to this. So we start with sigma x plus sigma y divided by 2, plus, then we do sigma x minus sigma y divided by 2 all times cos 2 theta. And then we add to that tau xy sine 2 theta. And that gives us the normal stress going in the x prime direction. And we would do the same kind of balancing, and we can derive the equation for our sigma y prime. And the only difference here is that it's the plus signs become negative signs. So if we do some of the forces in the y prime direction, we can come up with this equation, which gives us our tau x prime y prime. And so we see tau x prime y prime is equal to the negative of sigma x minus sigma y over 2 multiplied by sine 2 theta plus tau xy multiplied by cos 2 theta. So we have all the equations we need now to figure out what the stress condition is in any orientation theta, simple stress transformations. So the one thing we do need to do is to establish a sign convention and a process by which we're going to do this. And so we show the sign convention here on the slide, and we see that orientation changes is going to be in positive thetas will be in the counterclockwise direction. Counterclockwise theta will take us from x to x prime, or y to y prime. We also see the sign convention for the stresses. So normal stress, positive is tension, compression is shown as negative, and our shear stress is positive face, positive direction, negative face, negative direction. Those are both positive. If they're opposite, so positive face, negative direction, or negative face, positive direction, they would be negative. And that would determine the sign of your in-plane shear stress. So we're going to substitute then the components of stress, which we have in the xy direction. So that's your sigma x, sigma y, tau xy, into our transformation equations. And that will allow us to determine the x prime y prime components of stress, or the sigma x prime, sigma y prime, tau x prime y prime. And again, just to make sure that we're using the appropriate sign convention, if there's one place where people tend to have a challenge here, it's getting the sign for the shear stress correct. So we're going to do a quick example, and so this is rather arbitrary. So we have a plane stress condition shown here with a sigma x of 300 kPa, a sigma y of 100 kPa, and a shear stress, tau xy, of 200 kPa. And we're just going to calculate what the components of stress are with the orientation rotated 22.5 degrees clockwise, which would be negative 22.5 degrees. So follow the link. Go through the example, and that should explain anything to do with, basic arbitrary transformation of stresses. Now, what we need to do after having done that is look for that special case where we're going to find the circumstance or the orientations where those normal stresses and shear stresses are at a maximum. And that's what the next part of this lecture is all about. So principal stresses then are those stresses where our normal stresses, one on the x prime face, one on the y prime face, are a maximum, or is our worst case condition. And so what we need to do is we need to figure out what angle rotation is going to bring us to this circumstance where sigma x prime is a maximum. And we do that by taking the derivative of the equation we have for sigma x prime and setting it equal to 0, and that will give us a maximum and or a minimum. And so using that transformation equation and doing just that, we derive this equation, which tells us the orientation of what we call the principal plane. And it says tan 2 theta p is equal to tau xy divided by sigma x minus sigma y, all divided by 2. And this is great because those are the three components of stress in the xy orientation. And it's now going to tell us what the orientation is for our principal plane, or the place where the normal stress will be a maximum on the x prime axis. The one thing to note is that the equation does have two roots. They would be two roots. One would give you theta to the x prime, and the other one would give you theta to y prime. So if we then substitute solutions for theta p1 and theta p2 back into the transformation equation, we come up with a new equation which gives us the ability to calculate directly what the value of those principal stresses are. And so we see sigma max, or sigma comma sigma min, because there's two solutions here, is equal to sigma x plus sigma y over 2, plus or minus the square root of sigma x minus sigma y divided by 2 all squared, plus tau xy all squared. So again, it's an equation in the components of stress in the xy orientation, and it's going to come back and give us our sigma max, sigma min. Now, sometimes you'll see these referred to as sigma 1, comma 2, or sigma max, comma min, just depends on the textbook that you're looking in. So these stresses are the principal stresses, okay? And they, sigma max and sigma min, are 90 degrees apart. So one is on the x prime axis and one is on the y prime axis. And the other thing that we know is that we will have no shear stress, or the shear stress will have a magnitude of 0 on the principal plane, or the principal orientation. So at theta p, we are going to get a tau x prime y prime equal to 0. So we only have normal stresses. Now, it's also very helpful to be able to determine what the maximum shear stress, maximum minimum shear stresses are. And so we go through a little bit of algebra here, and we can actually come up with an equation that says tan 2 theta s, where that theta s represents the orientation of your shear stress, maximum in-plane shear stress, is equal to this equation, the negative of sigma x minus sigma y over 2 divided by tau xy. And so with that, we can get the orientation of our maximum in-plane shear stress. And we don't normally use this equation too much, because already having figured out that what our theta p is, we know that the maximum in-plane shear stress occurs plus or minus 45 degrees from the principal plane. So it's easy enough to calculate what our theta p is, our orientation of our principal plane, and then just add plus or minus 45 degrees to that to get the orientation of our maximum in-plane shear stress. So the actual value then of our maximum in-plane shear stress is shown here as tau maximum in-plane is equal to the square root of sigma x minus sigma y over 2 all squared plus tau xy all squared. Now, you've seen that before. That was just one of the two pieces of the equation which we use to calculate our principal stresses. So if you're paying attention, you can kind of do it in bits as you're going through, because that bit is useful in itself. And again, that just to summarize, we know that that occurs 45 degrees from the principal plane. So the one thing that's different, though, with the maximum in-plane shear stresses is that the normal stresses are not equal to 0. So remember, the principal stresses we knew that the shear stresses were equal to 0. Well, that's not the case here, but the one thing we do know is that they're all the same, and you're going to have the same value for normal stress on the x prime axis as you do on the y prime axis if you're on the orientation where we have the maximum in plane shear stress. And the value for that is equal to the sigma x plus sigma y over 2, or the average of your stress components in the xy orientation. Now, this too is a piece of that equation. There was two pieces of the equation to calculate their principal stresses. So this is the other piece. So one gives you the value of your maximum in plane shear stresses. The other piece gives you the value of your normal stresses on the plane of maximum in plane shear stresses. And so this is the process that we normally go through. We don't normally do a lot of arbitrary transformations, but what we do routinely is try to figure out what the principal stresses are. And so in this example, again, we're going to use the same plane stress element that we had before where we did the transformation of stresses. Only in this instance, we're going to very specifically look at what are the principal stresses, i.e. what is the orientation and magnitudes of the stresses that are the worst conditions that we need to consider. So what are the maximum normal stresses, what are the maximum in plane shear stresses, and what are their orientations. And so if you follow the link, go through that, and you will get a stepwise solution to this problem using the equations that we've just gone through. Now, that's about all we have. There's a number of different ways that we can find ourselves in circumstances where we have to arrive at this stress condition and then go on to look at principal stresses. And so the next bunch of examples are really those culminating examples for the course where we look at different circumstances and try to figure out what the stress condition is, and then you can go on and add to that by looking at the principal stresses. And so the first example is one of eccentric loading on a column, and I don't have the link to the solution of this yet, so I'll have to write that in at the bottom of the video. So just hit the view more in YouTube and drop down, and I'll put the links into these videos, and you can go through the stepwise solution for that. And this just shows you what it's all going to look like when you go through it and you break it up into its components and you see. But again, if you go through the solution, you'll see that. Then we have a couple more examples, a few more examples where we just look at complex loading conditions, break it up into its parts, get the stress at a point or points to be considered, and then as you can see, it would make sense to go on and do the principal stresses in those cases. So here's another example. Again, I'll put the link to its solution down below. And then we'll finish off with this one, which is probably about as complicated as it gets. I really work this one to try to get you to visualize the complexity of the 3 dimensions going on. And like I say, it kind of culminates the entire course in this one example. So I hope you enjoy it. Again, I'll put the link to the solution down below. And we'll hopefully see you later for some more advanced examples. And there are, on the YouTube page as well, there are a bunch of other examples that have been added over the years on review questions and stuff like that, so they can just add to your understanding and appreciation. So hopefully you enjoyed the series, and we'll see you if we come back and do some more.